Alright, welcome back. We continue and finish chapter 7. We're gonna apply matrices to transformation and focus on 2 by 2 and 2 by 1 matrices. Let's go and start with identity matrix. So first is definition of a square matrix. We'll have the same number of row and columns, and we'll restrict that to a 2 by 2, and an identity matrix has to be square. So if it is a 2 by 2, it will have zeros everywhere except on this diagonal it will be only ones. And what it means is the property is if you multiply by any matrix A, so here for example A is a 2 by 2 which with those specific values, if you were to do the working out and multiply by I, A times I will still give you the same matrix, and if you change the order you will still get the same matrix A. And these results hold for any square matrix multiplied by the appropriate multiplicative identity. With real numbers, it's the same idea as multiplying a number by 1. You can multiply by 1 on the right, and on the left you still get the same value. 2 times 1 equals 2, 1 times 2 equals 2 as well. So the purpose of the identity matrix is basically do nothing, right? But we'll use it later as a property related to inverse matrices. Here we have a 2 by 2 matrix A. We want to find out, is there such a matrix B so that when you multiply, whichever from the left or from the right, it will be equal to the identity matrix. So they will start with an unknown B matrix. They will make it equal to I. They write the system and they do the multiplication. It's a simultaneous linear equations. They want to find the values of x, y, u, v. Here we will set up, it will generate 4 equations as we have 4 unknowns. As you solve that, we end up with this matrix with decimal values, and it will show that if you multiply from the other side, it will still be the identity matrix. That specific matrix is called the inverse of A. Alright, so keep that in mind. Let's go with the general definition, and now let's go back. That the way it was done in that example, you won't have to do that again. There will be a better method, and the better method comes down here. If you have a matrix A and you have the values A, B, C, D, the inverse is you multiply by the reciprocal of that value. It's AD minus BC. The way to do it is think about a cross. It's a cross product. So it's AD minus BC. Okay? And that matrix, the way it's rearranged, you started with AD, you swap around those values, okay? And the other diagonal, you just get the opposite value by having a negative sign in front of it. Now remember, we can't divide by 0, so as long as that denominator is not 0, then the inverse of that matrix A is annotated that way, and it is unique. It means there's only one solution. Okay? Now that specific expression, AD minus BC, keep that in mind. It is called the determinant. It's annotated depth of brackets and the matrix. So here it's a reformulation of the determinant. And as long as that value is not 0, then the inverse matrix exists. So as definition, a square matrix is said to be regular if its inverse exists, therefore the determinant is not zero. And the opposite is, if you have a determinant of A is equal 0, it means you can't inverse it. That matrix is said to be a singular matrix. Okay? The general situation will deal with regular matrices, as we want to lead up to transformations and we need the inverse. Alright, let's do some application of what's been done before. The first one is to find the determinant of that square matrix. It is -1, so it is a the inverse exists, so it's a regular matrix. Let's go back to the formula. So if A has that form, the inverse is 1 over the determinant, so it's AD minus BC, which is calculated in part A. And for that matrix, we move across the 5 and 1, which is 1 and 5. And then the 2 and the 3 will become -2 and -3. Now the 1 divided by -1 is simplifies to times -1. And when we multiply by a scalar, we multiply by -1 every single entries of that matrix. So that will become the answer. Alright, next one. Again, very similar. You have a matrix. First, find the determinant. It is not 0. So the inverse matrix, basically A is a regular matrix. The inverse, you apply the formula to determine that matrix. We keep part B. For part C, what we need to find out is A. We have A times X equals that matrix, so 2 by 1. We want to find the matrix X, which is going to be a 2 by 1. Remember, when you multiply a matrix by its inverse, it's equal to the identity. So we multiply by the inverse of A from the left, so it's close to the A, and that together will give us hang on, let me go. Alright, so the left hand side simplifies to X, okay, but before we, and the right hand side is the inverse of A times 5 and 7. Then we need to evaluate that. So we have our inverse of A, which is over there. We're going to substitute that into here, which is what we have there. We multiply the two matrices, and then we multiply by the scalar, and we have the X matrix as a solution here. So that was it for 7F, which is the inverse of a matrix. We do 2 by 2 and the determinant. Let's move on to link that to transformations. So do remember the rules when we have those are the list of transformations we looked at. So let's look, for example, at a reflection in the x-axis using the mapping equations. This is what we had. Now we're going to slightly rewrite it, so each of the x prime y prime is in terms of xy and xy. So we introduce a 0 coefficient, okay, and we're going to do that for all the transformations. So we have the two reflections depending on the axis. Dilation of factor k from the y-axis, we multiply x by k. Dilation from the x-axis, we multiply y by the factor k, and then we introduce the 0 coefficient here. Okay, so we want to have both variables on the right hand side of the mapping equations. And the last two we looked at, we look at a reflection from the diagonal line y equals x, so we swap the coordinates around, and also the translations, horizontal translation, vertical translation, in that way in those equations, okay, and we're going to link that back to a column matrix. Okay, so here's the general situation. we have a mapping of equations, so x prime, y prime, and we have written that over here. This is what we call a linear transformation, and we can reuse that, write this as a matrix equation. So those coefficients now, a, b, c, d, will form the transformation matrix, a 2 by 2. The variable from the original and the image will be written as column matrices, 2 by 1. Okay, and this is equivalent to that mapping that we had before in the mapping equation. So we're dealing with, we have our transformation matrix, and we can apply that to the previous transformations we dealt with. So when you have a reflection and we write the rules in terms of x and y, you have 1, 0, 0, negative 1. That becomes our transformation matrix. We do the same for all of them. So you can see for reflections you have a negative 1 strategically positioned. With the dilation as well, on the diagonal you will have a k-factor depending from which axis you're at. If you do a reflection from the line y equals x, you have that. It looks like an identity matrix, but it's not. It's on the opposite diagonal. So the application, let's look at a few examples. Reflection in the x-axis. So what you would do, you look at the reflection in the x-axis, you identify your matrix, and you multiply by the 2 by 1 matrix to get the image coordinates. Dilation of factor k from the y-axis, you get your transformation matrix. You do your multiplication. Again, you should be able to do that by hand, and you get a 2 by 1 matrix. And that's your transform, the mapping of the coordinates from your original to your image. Now, we have two linear transformations, so we have 2 points getting respectively transformed. You do not have the transformation matrix, so you need to solve your simultaneous equations, and you're going to have 4 unknowns. Once you've done that, you can apply the matrix equation to determine the image of that. So first part, make your transformation matrix A, B, C, D. You multiply by the first point, you multiply by the second point. That gives you your first 2 equations. And your second 2 equations, they're simple enough so you get straight away your values A, B, C, D, and now you have your matrix down here. And then to find the image of that coordinates, you're going to multiply this matrix with the original coordinates. You do your multiplication, you simplify, and those are the coordinates of your image. Alright, last bit is composition of mappings. If you have 2 linear transformations, we can compose or do them one after the other one, each transformation by simply multiplying the matrices. Okay, so if I multiply BA, it means that, and the order matters, so it's not AB. BA is you start with A is applied first, and then you apply the transformation B. Okay, so you BA from the back, you start with the transformation A, and the second is transformation B. Here is the complicated expression. It's basically the product of the B by A. It'll make more sense if you use numbers, okay? Notice B is a 2 by 2 dimension, A is a 2 by 2 dimension. So when you multiply them together, B times A, it's also a 2 by 2 matrix. Alright, you have 2 transformations. You have the first one, which is a reflection, and the second one is a dilation. So go back to your mapping table find your matrices. So for the reflection, this is the first matrix, and for the dilation, here is your second matrix. Multiply them together to combine them as one. K is a variable, which is fine, leave it as it is. You're just going to have an answer in terms of K. Your original point is 2, -3, so you write it as a column matrix. You multiply by BA from the left. You substitute with the appropriate matrices that you've done above, and you get 2K and 3. Those are this is the image point. All right, last example. So have a look here. It's made up of two transformations. The first one is a dilation of factor K from the y-axis, and then you have a translation defined by that matrix AB. Now, it's not that translation is not a linear transformation. Therefore, the way it works out is, let's say we call A the transformation matrix that is linked to the dilation. So A is going to be that one. Okay, and what you know is when you multiply A by X and then you add the translation matrix, you end up with the image point or the image matrix. Okay, what we want is we want to find an equation in terms of the two equations in terms of the variables. Okay, so what we're going to do is rearrange it to make, we transpose all that to make X the subject. We're going to multiply by the inverse of A. So down below we have A. The determinant of A is K, so it's not 0, otherwise it would be it wouldn't be a dilation. We can write the inverse function, and what we do, we're going to operate the multiplication down here. So we're going to substitute the inverse of A with this matrix, C with AB, and we're going to get sort of formulas in terms of there's going to be K, AB, XY, X prime, Y prime. So we substitute, we combine. It's a difference of matrices, so we can combine it as a 2 by 1 by doing the difference of the entries. Then we need to multiply by that 2 by 2. That gives us that answer. And therefore, we can write those equations. Now, it doesn't say, actually it does say that X and Y have to be the subject. That is why we need to do that transposition to make X, the matrix X, the subject. What you could have done actually is substitute straight away from here. Okay, evaluate the left hand side and then come up with those two equations in terms of X prime, Y prime, and then for each equation rearrange it to make X and Y the subject. So that method would have worked as well. And that's it for today's session and also chapter 7. I'll see you later.